We all know semantic word embeddings, which store in some sense the meaning of a word in a fixed-sized vector. Today we'll look into phonetic word embeddings. We'll first go over what those even are, because they are not as known in the wider NLP community. Then we introduce a few tasks that we believe are a good measure of phonetic word embedding quality. We'll also describe a few basic embedding models and implement the simplest one together. Word embeddings are nothing new in modern NLP. We have strings, and the word embedding function f turns them into fixed dimensional vectors. The dimensionality is arbitrary, most commonly 512, but importantly remains constant for all words. Once we have these vector representations of words, we can do many things with them, such as using them as features for NLP models. Conceptually, we can imagine that each word is placed somewhere in the vector space, and that the words that are similar in meaning are close together. Phonetic word embeddings are not that different. It is again a function f that transforms strings into vectors. However, instead of words being placed in a space based on their semantic meaning, they are placed based on their phonetic properties. In this case, for example, ocean is closer to motion than to wave, because the pronunciation of ocean and motion is very similar. Beyond linguistic analysis, phonetic word embeddings already found their use in many applications. Cognate and loanword detection is more easily done with pronunciation representation, and similar holds true for multilingual named entity recognition. Phonetic representation makes models more robust to orthographic variations, which has been used in key phrase extraction and spelling correction. There are many more, with poetry generation of course being on the list, as it benefits greatly from the extra pronunciation information. Our goal is to build an evaluation suite for these embeddings. Without it, we don't know if the field is making progress in the right direction, and also it's unclear to newcomers which methods are the most promising. For this, we designed 5 varying tasks that we believe point to the strengths and weaknesses of phonetic word embedding methods. We packaged these and a few embedding models into the phonetic word embedding suite. The first task is related to sound similarity. From human studies, we can get some consensus that, for example, ocean sounds 70% like motion, but only 2% like soybean. Screech is also not similar to plant, and sick and sit sound close. We can formalize this into a function sh. Now recall that our phonetic word embeddings produce vectors. What we'd want is that the vector similarity given by SV of these vectors is similar to the human sound similarity sh. The vector similarity can be either cosine similarity or negative L2 distance. And the scale does not matter because we evaluate the performance on this task using correlation. That is, we want a pair of word vectors to be close together if and only if they are also judged by humans to be close together. Only if the embeddings are good ones will the correlation be high. We have only a few human annotations, which are also only in English, and to be able to extend this to also other languages, we use articulatory feature distance, which computes based on phonemic features the similarity of two words. The second task is closely related to the first one. Recall that we can imagine each embedding being a point in space. When we focus on a single point, such as motion, then we can expect words that have similar properties, such as that they sound the same, to be close to it. In this case, lotion is the nearest neighbor because the pronunciation of motion and lotion is very similar. On the other hand, words that sound very differently, such as brave, are far away. To capture this desired behavior as a task, we compute the average rank of the closest sounding neighbor. From the articulatory feature distance, we know a priori that the closest neighbor to motion is lotion. So we then look into the embedding space and check how far it is from the anchor motion. Mathematically, this corresponds to computing the average rank, which we normalize to span from 0% to 100%. The third task is a bit more practical. It comes as no surprise that some words rhyme, such as the ocean and motion or bean and queen, while others don't, such as ocean and soybean. We can turn this into a task. Do the phonetic word embeddings encode whether two words rhyme? This is a bit tricky because different embeddings encode things differently. To be fair to all of them, we use the embeddings as input features to a deep neural network, specifically a multi-layer perceptron. Then we train this model to perform the classification into classes rhyme or no rhyme. The better the embeddings, the higher the final test performance of this classification model. The next task has a very similar setup. Lexical cognates have the same etymological ancestor. An example is the English word plant and the French plante, even though orthographically equidistant, plain and plante are not cognates. There are many false friends. For example, English much is not related to the Spanish mucho, even though they mean related things. And determining whether the two words are cognates is easier done on the phonetic level, such as in the second example. Therefore, we would expect phonetic word embeddings to be a good tool for this. Similarly to the previous task, we use them as features into multi-layer perceptron that classifies as either cognate or no cognate. Then we measure the embedding utility by the final model accuracy. The last task draws inspiration from semantic word embeddings. There, we all know the example that we can use it to compute analogies, such as a man is to woman as king is to queen. Computationally, this is achieved by subtracting the vector for woman from the vector for man and adding the vector for king. Then, the closest neighbor to this computed vector in our vector space should correspond to queen. Formally, there is a transformation happening on each side of the equation. And we are changing the gender and turn the man into a woman. We then apply the same transformation on the right side by turning the king into a queen. We can do the same thing for our phonetic word embeddings. In this example, we change din into tin by removing voicing from the first phoneme. On the right side, we expect the same thing to happen and we change from zin to sin by removing voicing. Again, we can computationally approach this by subtracting tin from din and adding zin. Then we would expect that the closest word in our embedding space would be sin. This already sounds like a task because we can simply count the number of cases where the lookup of this transformation was successful. Now we know what tasks we expect our embeddings to solve, so let's go through 3 phonetic word embedding models that solve them. The first model is rather baseline, and we will implement it together at the end of this video. It is simply a vector that counts how often a particular phoneme occurs in the string. On the first position is how many times S appears, then how often the short U appears, and so on. For the word soybean, the phoneme S appears once, so we put a 1 in the first slot. The short U does not appear there, so we put 0 there, and same for M. However, B occurs once, so we put a 1 on the 4th position. This way, we can turn any string into a fixed width vector because the template is predefined beforehand. Despite the simplicity of this method, we can already see that words that sound similar have similar vectors. Ocean and motion differ in just one phoneme, and their vectors are the same except for one position. The count-based approach is perhaps too simple because it does not take relative positions into account. A common tactic to represent a sequence is to use the encoder-decoder architecture with a bottleneck vector. In our case, we use an LSTM model and feed it the first phoneme. This creates a vector representation which we can use as the input, together with the second phoneme into the second state and so on. At the end, we have a single vector, which we use as the input to the decoder, which we ask to produce the first phoneme, then the second one, and so on. Of course, we can use this approach for words of arbitrary lengths. We can then optimize this method by computing loss for the decoder to make sure that the identical word is decoded. Then, for inference, we only care about the encoder part that gives us the vectors. The autoencoder has some drawbacks, such as that it only cares about reconstructing the word, but not really about the phonetic representation. Recall from the first task that we know what the pronunciation distance between two words is, and that we are asking the embeddings to be positioned such that they have the same distance. Well, we can use that directly in our optimization objective. Our loss would then be the difference between our current distance as predicted by our model and the goal distance. Only when we minimize this loss will we get the same distances between embeddings as humans perceive them. This is not the most sophisticated model that we have to offer, but will suffice for demonstrative purposes. Our test suite contains phonetically diverse languages. It has English, Amharic, Bengali, French, German, Polish, Spanish, Swahili, and Uzbek. 2 of these languages don't use Latin script, and for each language, we have about 200,000 unique words. Now let's look at the main results. The overall score is just a simple average across the 6 separate tasks. We first start with semantic word embeddings that people typically use, such as those from birth. On almost all the tasks, the embeddings fare very poorly. 50% for rhyme and cognate detection is equivalent to a coin flip. In contrast, our models specifically for phonetic representations perform much better, though there is still big room for improvement. Now I'd like to walk you through how to build your own simple phonetic word embedding model, and how to evaluate it using PWESuite. We start with cloning the evaluation repository and installing it. Then we load the dataset, which is only one split. We can see that the elements of the dataset contain cognate information, such as its orthographic, IPA, and pronunciation representations, and its original language. Now we use count vectorizer from the scikit-learn package. We set the number of max features to our desired dimensionality, which is 256. We want each character to be counted individually, so we use the character analyzer. And finally, we are interested in character n-grams, which give us some information that is otherwise lost. We transform the whole dataset and see what the individual extracted features are. We can also see that we now have 2 million arrays, each of size 256. Let's save this and run the evaluation, which takes a bit of time to compute. At the end, we are given the embedding score across the tasks. This particular embedding that we created performs quite well, with human similarity and rhyme detection, but nowhere else. It is not a very good embedding, but hopefully serves as an illustration how to use this evaluation suite. This concludes our phonetic word embedding journey. I hope you learned something about the evaluation tasks, but also the specific models, and maybe got some idea for your future work. In the future, I would like to see new tasks to test these embeddings, but also more elaborate models. Finally, the embeddings could also be used to study interesting linguistic phenomena in themselves, such as phonotactics learning. Thank you for watching this video.